In this presentation, I'm going to show you how can you run a simple conformation analysis. And afterwards, if we know some specific reaction coordinate, we're going to look how we can also further study it and create Markov models out of it. So, okay. So the first example we're going to use is from a project we had, including a chemokine called CXC12. CXL12, and it's the ligand of GPCR. So most of you are working with GPCRs, and well, this is the ligand. It's not the proper GPCR, but it's also interesting. So it's related to many types of cancer, inflammatory diseases, and that's why it's lots of interest lately. And the data set is it's made of 300 simulations of 200 nanoseconds each, so it gives a total number of 60 microseconds in total. This is the chemokine. Chemokine has the C-terminus alpha helix and a disordered N-terminus, and it has a very specific beta sheet, as you can see, 3 beta sheets, and then there is a specific turnover there. For this specific project, we're not so interested about the movement of the tails because they are pretty random. This unfolds a bit. I was more interested in see if there was some pocket opening in the core of the protein. So it's a metric we're going to use afterwards. It's not going to include the tails. It's only going to include the core. So let's start. So you can. I recommend you to check the HTMD website. I don't know if they have told you before, but the documentation is getting updated constantly. But I would recommend you to look at the tutorials, try to see which is the, depending on what you want to do, what's a tutorial there that fits more what you want to do. And for example, here there's a crucial step before this, which is the filtering of the simulation that I'm not doing right here. But you're going to find information there how to do it with your trajectories. If you don't have ecstasy trajectories, I don't know if DCD is supported right now, but you can easily find some kind of conversion. Yeah, conversion. And you can try it with your own systems afterwards. So first of all, I'm going to try to view molecule. So after filtering trajectories, what it's producing is a list of trajectories, so folders with trajectories inside, and then it's yeah. So yeah, filter is, well, you can filter according to your own criteria, but usually it means that there is no water because water is there. We are not usually interested in our tank. And it was taking so long, probably it's because of the WebGL. Let's restart this. Can I restart it? Yep. Oh. Actually, I'm going to present like this. I'm in presentation mode. Okay, let's see. Alright, so here's the molecule. Filter one. Okay. So as Noelia did, first of all, we have to make a sim list, which is basically we're telling them, hey, this is the list of trajectories that we want to use, and this is the PDB I want you to use to represent those trajectories. Once you filter the trajectories with sim filter is another function you're going to find in the tutorials. It's automatically producing this filter.pdb. So we're going to run that. Okay. So now comes the interesting part. When we were trying to analyze what's the conformational change of a protein, there's several metrics we can use to do that. We used to use contact maps between the carbon alphas between them, and also distances. But one metric we have found that it's very useful is the dihedral, so how the dihedrals move, the angle, the phi and psi angles, how they are moving. And that's what we're going to do, and it's pretty straightforward to do. You just have to call this method dihedral.project. We pass the list of the simulations that we have created. We just tell him the selection we want to create the, well, we're about to calculate the rotations of the dihedrals, and we just have him sync to. As I said, I'm trying to avoid the terminus, so the C and the N terminus, and that's why I'm making a selection of 10 to 54 residues. And then here I'm explicitly saying each of the steps of my simulation is 0.1 nanoseconds. I think this is the default value also, but it's never too hard to put it explicitly. And this is probably the steps going to take more time. And we're talking about 60 microseconds of simulation, so quite a lot. And we can also plot the trajectories to see what I said at the beginning was true. All right. Let's see. All right. So yeah, it's almost 100 simulations, and there are 200 nanoseconds. Each of the frames is 0.1 nanoseconds, so it's 2,000 frames in the end per simulation. Now we're going to use Tika. I'm probably not the best person to answer questions about Tika, as you can probably imagine. It's pretty complicated, but the default values, as we said before, is to use 20 frames here, and you're gonna do it with 3 Tika dimensions. You can start doing with 1, and then see the model. If it's good enough, then go to 2, 3, etc. Is there any error so far?
No.
Okay, success then. So we're gonna do some cluster. We use this method, really batch, really nicely, and we're gonna do with 200 clusters, and we use the merge model, as Noelia said, to merge the clusters that have less than 5 counts, 5 frames. We join it to the next neighbor. All right, it's working. Now we're going to create an instance of model, and we're going to plot the timescales. This is the range we're going to use. And this plot should tell us which is the slowest process, and it's going to help us to choose which is the lag time we should choose to make the Markov model. And also it can tell us more or less how many slow processes there are, and depending on the number of slow processes that we're seeing, then we're going to put more or less the same number of macro states if we want to differentiate them.
So a question. Here we use Tika to apply it on the data, and data is a metric dihedral.
Yeah.
It means so it's like a principal component analysis for the dihedral subspace. So what kind of data we make analysis using Tika? It's a dihedral. What was the related to the dihedral?
If I'm not mistaken, you reduce the dimensionality, and for example, we had contact maps before, which were, I don't know, like 50 per 50, we're doing some self-analysis. And in the end, we end up, for each frame, 2 numbers, basically, which are from first dimension and second dimension, right?
3 in this
You
case.
could say, in this case, it's 3 numbers. So we are getting from a space where we have, for each residue, we have 4 numbers, right? Which is the cosinus and the sinus of the psi and psi, the phi and psi. And we project that to three Theta dimensions. There's no more information I can give you right now. So, success, we have the timescales right here. We usually would pick a timescale where the model is converged. That means that this is flat. So in this case, maybe it's a bit too extreme to take 80, but we're gonna take, well, this is in frames, so it's 800. But you can pick a bit before if you want. And I'm gonna pick 8 states because I'm interested not only about this timescale, which looks pretty slow, but also I'm interested about this one. And I'm going to plot the equilibrium distribution. So what we're doing right now is making a Markov model at this particular lifetime. And we are clustering all the micro clusters that we did before. We're macro clustering them into 8 macrostates. So 8 big groups of microstates. All right, so here we have for each of the macrostate that we created, which would be the equilibrium population. You can see that the state number 7 is the more populated, and then there's a couple of them also. So right now, let's try to view the states and see why they are different between them. Takes a bit of time. If you didn't kill the terminals, as I told you at the beginning, you probably have some error here because of memory error. Okay, then it's my fault now. I killed them. All right. But let's suppose that maybe you are lucky enough and you can see them. Yeah, it's working for you?
Yeah.
Great. So, for example, we can visualize what are the difference between the macro number 7 and macro number 6. You can probably see that the macros are not really different from each other. They have very small differences, but they are actually captured by the Markov model. And you probably, in this case, you would be interested to see the surface and to see if one of those macrostates is showing any cavity that we could use, for example, for like drug design, etc. And also, if you could check probably one of the macrostates, the 0, if you can check the number 0, you probably see that there's an opening, the number 0 and the number 1, there's an opening of one of the beta sheets, which is a process that I'm going to talk about it later, but it was pretty interesting. I was interested to find it. So, well, imagine you want to see the differences. You just look at them, the macros, and you say, okay, I don't know what are the differences. I can see it from the picture. So you can make the plot that I'm proposing here, which is telling you the differences between the macros in dihedral terms. So let's say, for example, I want to see the differences between the macro 7 and the macro 6. And I want to know which residues are involved in such differences. So here you can see that the differences are related to residue 16 and 17. And here it's telling you which angles are involved in the differences. Okay. So we could try, I'm not sure if it's going to work. We could try to visualize these differences, for example, 17, 16, 17, 24, 25, okay? And here, okay, so here we can see. So we can see that the rotation we are capturing with our Markov model is including the residues highlighted in this plot. It's not a big movement actually, but it's taken as the slowest process in our case. So imagine you probably find specific state that you're interested about and you want to know which state, which trajectory produced the state that I just saw. For example, I want to know from my macro state number 6. Can you tell me which micros they are inside? And he is telling me, okay, micro number 10, 21, and 60 were inside the macro number 6. Okay. So now I want you to give me with the sample states. It tells me, okay, now give me 10 trajectories that visited this state. Here you have, this is the absolute number inside the seamless, and this is the number of frame that visited the state that I just found. So let's say I want to know which is the name of the trajectory that I just found, visited this state, and he's gonna tell me it's the filtered 9x9 blah 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 dot xtc. So I could go to that trajectory and see in which moment he visited the state that I just found. Which of them? All right. So now we're going to study a different. Did it work for all of you more or less? Yeah? All right. That's good. So now we're going to take a different reaction coordinate. So say that this is a real case. Say that you read the literature and you see that some guys have made some simulations with Amber. We are simulating in Charm, for example. And say that they have found the movement and the opening of a pocket between the second and the third beta sheet, right? And they are able to define this is closed and this is open. So if you place the molecule, if you visualize it, this is the terminal C helix, and the N terminus will be around here. So I just want to know, okay, did my simulations sample the state? And what would be the equilibrium distribution? Is it as frequent as they see? Because they made this very long simulation of 1 microsecond, and they actually saw the state happening quite often. So I just want to know, did my trajectories produce exactly the same result? So there's a way to know if you download HTMD on your local machine, you can do this kind of selection with VMD. But I will try to do it here with the HGL. And I'm interested with the opening of these two beta sheets over here. So say I want this column, it's written somewhere.
Yeah, but it's
Okay, I cannot see it, but all right. So I will just, yeah, well, that's it. Yeah. Okay. So imagine here, say 42 to 30, okay, more or less, 38 to 42, right? I want to see, this is my first selection, and the other beta sheet, I'm going to select it from here, which is 20 to 38, 20 to 22, 28. Probably I made the selection a bit more up. Well, the thing is that I want to take one selection for one of the beta sheets and the other selection for the other beta sheet, because I want to see the distances between both of them and see if they're opening or not. So right now I'm using this method called metric distance, and I'm passing the simulations, the simulations that we did before. I am making the first selection, and I want to calculate this distance between the first selection and the second selection. And I'm only selecting heavy atoms by using this unknown H. All right? And I'm saying I don't want the distances, I want the contacts, which is it's kind of a simpler approach, but we have seen that it's more powerful, which is basically when they come together closer than 9 Armstrong, then you count that as a 1, and if they are not closer than 9 Armstrong, then you count it as 0. And then you have a matrix of 0 and 1s of the contacts, right? And I'm defining again 0, 1 as the step. So let's run that. gonna take some time, I believe. This one is a bit more expensive to do. I'm gonna put already TK projection. As you can see, I'm using exactly the same parameters. You could try others, try to refine the Markov model, maybe some other parameters are better for you. Just try them out, see usually the way to assess if a Markov model is well done or not is to check the timescales. If they are,
This takes 5 minutes.
TK.
yeah, the TK is pretty long here. It's pretty long. Yeah. But believe me, 5 minutes is not so much. I have some systems that take like 15, 20 minutes, depending on how large. Right now it's a covariance, so it's kind of calculating for each of the rows and the columns, which is the covariance. So the bigger the matrix is, the larger time it's going to take. So I'm going to use same command, the cluster, 300 clusters in this case. And I'm also going to plot the timescales.
Well, I would say it's worth it doing TK usually because it improves the Markov model a lot. So even if it takes 15 minutes, you're sparing lots of time afterwards, which you would waste in your analysis.
It's going faster after TK also.
Yeah.
That's why it's worth investing 5 minutes of your life on that.
So is TK multi-threaded? In other words, if you have bigger computers, it will be faster. Or
Stefan?
Yeah, I think the last version that they make is multi-threaded.
I think it more depends on the number of the CPUs or on the memory.
Actually, I don't think TK itself is multi-threaded, but I think it uses BLAS, so for the linear algebra, which is using, I think, multiple threads. Sorry, what was the question?
What kind of the computational resources used the calculations of the covariance matrix here?
These are just matrix multiplications actually, and yeah.
It's the CPUs. CPU.
What's used? Yeah, it's on CPUs. Sorry, yes.
I have an issue now because the Python version is using the Panama feature, and it's substantially slower than our MATLAB version, and like 20 times. So how much slower was it?
No, not so much.
Substantial.
No, I think it was like 3-4 times.
3-4 times.
4 times slower than. We can't understand why.
Typically, MATLAB is faster, yeah, for the same kind.
Yeah, but really they're using the same thing in your needs, so they should. I mean, MATLAB covers better edge cases. If you have integer data, they must do something to use plus anyway, and so in that case you get 20 times faster in MATLAB than Python. There's no plus for integer. But normally you can recover. In this case, you couldn't. So we told them that it's 4 times lower and you still are 4 times lower. And in the future,
I think it also depends, I think, on the number of trajectories you have and their length, because probably if you have more trajectories, then you're wasting more time like looping over them instead of doing matrix multiplications. So
it's initially all of the trajectories are merged into the one trajectory to produce covariance matrix.
No.
Or it's for each trajectory new covariance matrix.
Yeah, it needs to
So
be for each
because it's
trajectory
all-
because when you're counting time lag correlations, you don't want to jump over trajectories and go
yes.
from trajectory 1 to trajectory 2 because the
So it's not possible to make the.
It is possible, but you need to take care of how you calculate it, and I don't know if it would be faster or not.
Typically, for the principal component analysis, initially we make the big ensemble of all of the trajectories,
Yeah.
from which we calculate the mean and etc.
Yeah. No, in this case you need to be a bit careful. I don't know if it would be faster or not, but yeah, it doesn't work so nice as with the PCA where you can just put everything into one array. It's neatly done.
Come on.
goes out to make it faster, it goes yeah. It is a 4 times I lose the game. So.
Hopefully the time scale is gonna be fast now. We need 60 microseconds of data. Let's not forget that.
I think like to make the integration with the time mode for the visualization because it's also using Python. There is
But I have a free version, but it's
education of the version which is for limited, but it's like the whole screen, which I Python Python.
Probably is not that yes. Somebody can.
That's the
This case,
all right.
I know, but his line is blastering already. He's ahead of me. Yeah, it's done, Gerard.
All right. We have the timescales more or less. All of you. Wait a bit. And I wait until they have the timescales. No, a bit. Well, whatever. So we do exactly the same thing. We look where the timescales are flat, more or less. Let's say it's 60 nanoseconds. Remember, if it's in frames, so you should put one more zero. And in this case, I'm interested about 1, 2, 3 processes, and let's say bulk process, which is going to be 4 in total. And so you can see that most, hopefully this will work. So macro state number 3 gets more than 80% of the population in equilibrium. 92. And I'm just actually wondering, will one of the states be the open state that I wanted to see if it was happening? And this is the population. That was my initial question. After this, you could probably calculate the kinetics. Also, there's all sorts of analysis you could do to assess other stuff. I think kinetics was not working before, so I'm not going to risk it. Not to risk. Let's see if we can see it.
It's visualized, but
Yeah. Maybe it has less memory or more terminals open.
we'll ask around. Okay, it works for the rest, so just
It's working?
Yeah.
So can you check if one of the states is the open one and which one is it? So it's going to be like 3 or 2. You have to look at the third beta sheet.
It's unfolded.
If it's open, the second and the third one.
No, these are closed. So
Okay, check the first one, 0, 1.
yeah. There's an open sheet starting.
So, yeah, this one is open. You see, this 2 is open. It's a very, very subtle thing, but it's a number 0, let's say, and the 1 thing also is open.
Yeah, one is open.
Okay. So, you can probably calculate the population is, I don't know, less than 3% or something. So it's pretty unlikely to observe this state, at least less unlikely as the publication that I showed you at the beginning, where seeing this opening pretty much often. So imagine for our publication, we want to create a plot similar to this one, because I think it's very cool and I want to do the same. Try to stop this because for some reason it's not running in our machine. Okay. So imagine the macro I want to observe is the number 1. Then I look. 48 is the only micro that was clustered inside the macro number 1. Use this function over here. Then I look. The trajectory that is producing the state that I saw is number 277. Okay, perfect.
From the pyramid.
And here is the trajectory that produced my state. It's filter number 10, x23. So it's loaded here. And now I'm interested. I can see the simulation, but probably it's not going to work for me, so you can try that. But I'm interested about the metric RMSD of the opening. So I'm gonna
Try.
Yeah, try actually visualizing. This might work.
Just random.
Yeah, it didn't work. The other thing.
Well, there was no view.
There was no view. Okay. Alright. Actually, I can do this, no?
If you want, you can view.
It's not loading.
Wait.
You, what I'm writing. And then I make which right.
Yep. And then a view.
And then in the end I can make my simu.bo. Let's try to do that.
Hey.
Right. So this is the initial state. You can see that they're both closed. And I'm going to go somewhere over here.
I think it's not aligned. The trajectory is not aligned.
It's not aligned. Okay, we can do that. My simu dot align, and it's going to take us in protein, no, as a default selection.
No. So put it selection.
Okay, so cell.
No, just protein.
Like that.
Yeah, just
protein. All right. So hard.
Type when you cannot see what you're typing.
Okay. So now should be aligned. You can see it's closed. And at some point, there you go. It's open. There's an open here. So now I'm going to try to plot it in a different way. I'm going to plot the RMSD. RefMol was the filter.pdb, which is the reference structure, is pretty much the crystal structure, which it's close to Pocket. And here I'm just making the same selection as before. I'm just saying these residues or the residues of the other chain of the other vector sheet. So I calculate the RMSD, and now I can make beautiful plot like this, and you can see how at some point it's opening and staying for the remaining of the simulation. Actually, I had it here to visualize it. Right, so that's the kind of the showcase part. If you have any question, all right, that's a good sign.
Excuse me.
Okay.
Sorry. The one that you showed earlier, this literature example, I mean this paper that you showed.
Yeah.
So they just did one very long simulation, I understand. And then
Yeah,
you observed this opening and closing of this loop, basically.
Yeah.
And in your case, you had
Very short trajectory of 200
several
nanoseconds.
simulations,
Yeah.
and in one of them you observe this opening, but you don't observe it closing again.
Yeah.
So can you use that to say anything about the kinetics of statistics there? Because
Probably not. Probably you cannot say much. You should simulate. If we were using adaptive, you would probably take this state as a starting state for new simulations, and from there you would sample the process better. These ones are not produced by any adaptive sampling or anything. They're just plain SEN 300. Okay, so this is the showcase. You can find another system, very interesting system. If you go to files here, Villain. So you can run it yourself. There is help. There's some spaces that you have to fill, and there's a bit of explanation. It's basically the folding of a small peptide, and hopefully you will end up with a state of folding, and you will know. I don't know if there is kinetics also. Let's see if that works, because before it was not working, but it's pretty much the interesting data that we are able to reproduce the kinetics of the folding of this peptide. So yeah, let's do that. Let's see if you have any problem.
The folding on Lean was produced. So this Lean initial data was given to me by Stefano Piano from Liscio. And I think they needed 45 micro or something like this to measure on and off. And we've done that in a few micro using the app, and you get similar data. Never worked in
Guys, if you need any help, just ask us, and we'll go around and help you.
It's following me. Wait, that's the same.